I am Keith Moffatt, Emeritus Professor of Mathematical Physics at the University of Cambridge and Fellow of Trinity College, Cambridge. Welcome to my exp. My own involvement in astrophysics started when I was a PhD student. My thesis topic was the interaction of turbulence with magnetic fields. Now that involves both the Navier-Stokes equations and Maxwell's equations for the electromagnetic field, and the very strong interaction between these topics in electrically conducting fluids. When you have currents flowing in these fluids, magnetic fields result, and the interaction of current and magnetic field affects the fluid motion. So it becomes a very complex interaction. And my own involvement has been primarily in explaining the field known as dynamo theory, explaining the origin of magnetic fields and the way they evolve in planets, stars, and even galaxies. If I take the Earth as a particular case, the outer core of the Earth is liquid. It consists of liquid metal, an alloy of iron and nickel. And it's in a very complex state of motion due to convection from the solid inner core, slow solidification process that goes on at the boundary. And that convection currents are very strongly influenced by rotation, the rotation of the Earth, the Coriolis effects in this liquid core. This gives rise to what I would describe as a form of helical turbulence, turbulence with this property of helicity, which we now understand in dynamo theory leads to a very famous effect known as the alpha effect. It's a sort of bootstrap effect whereby motion across the magnetic field gives rise to a current. That was something understood already by Faraday. And the current gives rise to a magnetic field, which can reinforce the magnetic field that you start from. So in that sense, a bootstrap effect, or if you like, a magnetic instability. So that gives rise to the generation of the magnetic field in the Earth. We're interested in the magnetic field for a number of reasons. In the case of the Earth, it does give us information. I mean, we measure the magnetic field variations here on the surface of the Earth, and by extrapolating downwards, we can infer the state of motion in the liquid interior. And that does give us a huge amount of information about what is going on there that we couldn't derive by any direct measurement. So understanding this magnetic or magnetohydrodynamic process is a very valuable tool in geophysics. And equally in solar physics, we have to understand the manner in which magnetic field, for example, can erupt from the solar surface. These eruptions are observed very frequently. They're capable of causing disturbances, electromagnetic disturbances down here on the Earth. We're fortunately protected by the Earth's magnetic field from radiation emanating from the sun. Without the Earth's magnetic field, we'd be in very serious trouble as a result of that radiation. And so for all these reasons, we have to understand magnetic field generation. There is a constant interaction between theoreticians and observational astronomers in the context of, for example, black holes and galactic magnetic fields more generally. I was involved with Donald Lyndon Bell in work trying to explain the jets that are observed emanating from accretion disks, which lead to the formation of black holes. And that is an area, again, where observation stimulates theory, and then theoretical work, analysis, usually of the equations of magnetohydrodynamics, stimulates renewed observation. So it's very much an interactive process, to and fro, between the two areas, the two specialisms.